outer space application. What I have set out to do is to try to give you a broad overview. I'm not an expert myself on this topic. I'm an engineer and a propulsion guy, so this is a little bit off topic for me, but I've tried to gather some information and tried to give you some overview of this area, a little bit from the outside in perspective, as you will see, and also a little bit, hopefully this will be a crash course for you in space systems overall, talk a little bit about orbits and things like that. Let's start with the big picture. The solar system, and I've done this a couple of times for school classes, and then I show a picture like this, and then I ask the kids if they can name all the planets, and usually they can do almost all of them. I will not do this test on you. We will take that as a lunch discussion. So I'll give it away right away. It's here they are. But my point is that the sun is a fantastic energy source, but the solar system is quite large, of course, and as you will see from slides later, we are very happy to be in the position where we are. It makes things a lot easier, and not only to live here, of course, but also to harvest energy from the sun and to work with the batteries, for example, to store energy on Earth or on satellites orbiting the Earth. Going in, it's hotter; going out, it's colder. That's one of the basic things. And if we look in more detail, I realize that you cannot read all this, but it's really the environment differs a lot across among the planets. And for example, if you look at the inner planet Mercury, temperature varies between minus 170 to plus 400 something, depending on day night. Of course, Venus, which has a dense atmosphere, has a more constant temperature, 460 degrees centigrade. That's quite tough, and the atmosphere is mostly carbon dioxide, and the pressure is very high, roughly 90 bars, I think. So. Venus or the Earth is as I said, very well positioned in here, with a nice temperature and a good environment. And going out in the system, our closest neighbor Mars is already quite cold, minus 140 to minus 35 roughly. So minus 35 is a daytime on the sunny side. And Mars atmosphere, do you know what that consists of? Carbon dioxide also, but the pressure is very, very low. It's only 6 millibars. So the atmosphere is very, very thin on Mars. And then going all the way out, for example, Neptune has an average temperature of minus 200 something degrees C, and it has an atmosphere of helium and hydrogen, some methane. Pressure is actually 1 to 5 bars. So reasonable pressure, gases we know, but very cold, and also very dark, because it's far from the sun. And if we look at the intensity of the light and scale it with what we have here on Earth, we give that a factor of 1. Then you see that already at March it's 43%. and that transfers more or less exactly to the amount of energy you can drain by using solar panels on Mars compared to in an Earth orbit. And interestingly, also you see how it drops down, and going out to Pluto there is essentially no intensity left to drain energy from the sun by using solar panels. So that, adding to the cold environment, it's really difficult to. I think it's obvious that you need something else than the standard method, which is solar panels and batteries. Another interesting thing from this that struck me when I looked at it the other day is that the intensity in lux which is what we sense, spans over a large variety of magnitudes. But if you look here on this interesting comparison, so 100,000 is a bright day here, a sunny day in Spain, I guess, and on Pluto it's what is this? Three orders of magnitudes less. Still, it's a typical. Our eye can handle this. It's like walking in a night-lit sidewalk. So the human eye is really amazing in handling this span in intensity. And we are not even the best creatures on Earth to do it. But again, you realize from this that the intensity in the sunlight is very low, going outwards in the solar panel, outwards in the solar system. Sorry. So that about the solar system and the environment and the difficulties there. Let's focus a little bit more on the Earth and the Earth orbits. This is an attempt to graphically represent all the satellites and objects that is orbiting the Earth. You see some interesting things here. You see this kind of ring here, which is the geostationary orbit. And typically in this equatorial plane of the Earth, at a distance of more or less exactly 36,000 kilometers, which happens to be the orbit where the period is 24 hours, meaning that a satellite placed here does one orbit in exactly 24 hours, meaning that standing on the Earth and looking at it, it appears to stand still. That's why this orbit is so attractive, and as you see, it's actually quite crowded. So when you plan to launch a new satellite here, you have to move the older one out of the way. So the ring is more or less full. Then you also see from this picture that it's quite dense, close to the Earth, and if you try to estimate the distances here, I said this geo ring is 36,000 kilometers, and what you see here, this cloud of satellites, is what we call the low Earth orbits, and those are typically between 400 and 800 kilometers. And there we have all kind of inclinations and orbits and all kind of applications. For example, the weather satellites is there, the International Space Station is there. all the remote sensing and Earth observation satellites are there that take images of the Earth every day. And so that is a very popular area to be in the space business, obviously, as you can see. And then you see other things in between, which is a little bit more sparsely populated volume, and in between, and typically halfway or somewhere in between, you find other things. For example, the GPS satellites and Galileo satellites. They are in higher orbits than LEO, but much lower than the GEO. And also in polar orbits to cover not only the equatorial plane but also the whole planet. And actually today, I will not talk about it very much, but the past few years revolution with the nanosatellites, the field that we are working in at Nanospace. Nowadays, actually, the whole surface of the Earth is imaged almost every day by hundreds of satellites taking images. So we almost have everyday coverage over the total planet. So that's how it looks. And now a little bit more details about the terminology. I mentioned this geostationary orbit, which is in the equatorial orbit plane, and then if you want to image the polar areas, for example, you obviously have to incline the orbit, so that's orbit inclination. And to get from the Earth to the geostationary orbit, you typically go with a rocket to this kind of elliptical orbit. That's called a geostationary transfer orbit, because most rockets simply cannot place a full-blown satellite directly into the geostationary orbit. There are a few exceptions, but typically you go into this orbit, and then the satellite itself, with its own propulsion, circularizes from this point and goes into that orbit. For all the low Earth orbits, they typically go there directly, being kicked off the rocket, and they're placed in the right orbit. But still, you want to perhaps spread them out. You want to control the distance between the satellites. So that's, if you come across all these words like station keeping, formation flying, it's about controlling the exact position of the satellites in the orbit. And believe it or not, drag compensation, there is actually drag in low Earth orbits up to 500-600 kilometers. If you fly there, and if you are a satellite, you will collide with single atoms of the atmosphere, and that will slow you down, and you will deorbit in a number of years from the higher levels, 600 kilometers. But as soon as you get under say 350 kilometers, it goes quite rapidly. And if you think with the International Space Station is located at roughly 400 kilometers, and that's for the reason that it's just high enough not to deorbit too fast, but still low enough that you don't have to carry all the mass far out. So, also as part of the crash course, I guess, we normally talk about the different class of satellites, and a large satellite is typically can be up to 7-8 tons and have a power level up to 30 kilowatts that can be generated from the solar panels typically, and these are typical telecommunication satellites in the geostationary orbit. So when we watch live television from the Olympics in Pyongyang or whatever, it's typically via telecom satellites that broadcast is. Then it goes down. Medium-sized satellites is typically 500 to 1,000 kilograms. Some of them are used for also telecom, but most of them I would say is used for science and Earth observation missions, taking images or radar satellites, things like that, looking at the Earth. Mini satellites, 100 kilogram range, was popular a while ago and used for Earth observation, technology demonstrations, things like that. But what has happened in the last 10 years is that the lower side here, especially the nano and micro satellites, has become extremely popular, and started out with this CubeSat standard that you possibly have heard about. They started out with educational purposes, but they are actually moving up into the real commercial applications, and also Earth observation and remote sensing, and even communication. Today there are clearly a hype in this industry. It's a lot of initiatives planning to launch hundreds of satellites to provide internet services or phone or constant imaging of the Earth, and they typically are using micro and nano satellites. And by the way, that's where nanospace is active also. We are providing these nano satellites with propulsion systems so that they can move around and control the orbit and do more advanced missions simply.